Yeah, so many thanks for the introduction and many thanks for having me in your seminar. So I guess I will approach this topic from learning theory from a different angle than the one that you are usually used to. So I think you should use the opportunity to interrupt me immediately if you want to know more about what I'm saying, and you should not just postpone all questions till the end. I think it's better to ask questions directly. So what I'm going to do is I will first tell you a little bit what the problem is that I'm talking about, and then I will tell you the approach or the direction from which we are approaching this problem. So, I mean, the basic setup in learning theory is very simple. You all know that. We have a typical question like this one. Given a sequence or a prefix of a sequence like 3, 9, 15, 21, you are asked to guess how the sequence continues. And of course, this only makes sense if the sequence follows kind of a rule. So if this is just an arbitrary random sequence, then the question is not really meaningful. And perhaps the most general kind of rule that you could expect here is that the sequence is computable. And so if the sequence is computable, then a possible answer to this question, how the sequence continues or what that sequence is, could be a Gödel number. So a Gödel number is nothing but a program for that computation that would produce the corresponding sequence. So, of course, it's well known that there is neither a continuous nor a computable answer to this question, because if you just have such a finite prefix, even if you know that it's computable, continuation could be basically still anything. So you cannot expect that this is a computable or continuous question. And actually, Gödel proved already in 1967 that you cannot even learn the Gödel number in the limit. So in the limit means you are supposed to produce a guess of a Gödel number, then you see more and more pieces of the sequence, so longer and longer prefixes. And then you are allowed to modify your guess, what the program behind that sequence could be. And so a computation in the limit would be a situation where you can change your guess, but eventually it has to stabilize and it has to converge to a correct Gödel number of the sequence. And Gödel proved that not even in this weaker sense, you can compute a Gödel number for such a given computable sequence. Now, my background is from computability theory, and in particular from a theory that we call Weihrauch complexity. And I will try to convince you in a few minutes that this is a very general and nice setup where one can try to classify problems like this one. In particular, in the theory, we can very well understand topological and computability-theoretic features of the involved problems. So what is the problem actually a little bit more formally? So a little bit more formally, we assume that we have some fixed Gödel numbering. So Gödel numbering is just a surjective mapping from natural numbers onto the set of partial computable functions on natural numbers. So that is often denoted by P. So that means every computable function has a Gödel number, and typically this is defined in a meaningful way, perhaps using some machine model or something else. We don't really care about how this Gödel number is defined exactly. We just take it as given. And then the Gödel problem that we want to discuss here is the problem that given some computable sequence P as an input, find some Gödel number I of it. And this is a multi-valued problem. So this double arrow here denotes multi-valued problems, because there is not just a single Gödel number which is a valid answer, but there is a whole set of possible valid answers for every computable sequence. So Gödel numberings, if they are standard Gödel numberings, then they are not injective at all. So typically there are infinitely many programs for any single computable sequence. So this is a highly multi-valued thing. This inclusion here denotes that it's a partial multi-valued function. So in this whole theory, we really like to talk about multi-valued functions rather than relations. So mathematically speaking, these are nothing but relations, of course, but we prefer this perspective of a multi-valued map because we really have some dedicated input and some dedicated output, the input being the computable sequence here and the output being a Gödel number. Now, there are other very closely related maps here. One is Kolmogorov complexity. So for our purposes, this is just the single-valued function that minimizes over these possible Gödel numbers. So that means it gives us the minimal Gödel number for any particular computable sequence. Sometimes in other contexts, it's defined slightly differently, but for us, this is what we mean by Kolmogorov complexity. Now, one motivation for this whole study was also to understand work by Weihrauch and Rogers. They, in their work, have coined the slogan that the only useful additional information carried by a program compared to the mere sequence of natural numbers that it computes is an upper bound on the Kolmogorov complexity of the sequence. So Weihrauch and Rogers prove that in a certain sense this is true, that if you have a program, you have more information about the sequence that it represents, and what that more is exactly an upper bound on the Kolmogorov complexity of the respective sequence. And so in this approach here, we try to see whether we can kind of put the slogan into a more formal version of a theory. Okay, now there are even two further variants which are motivated by that slogan of Weihrauch and Rogers. So they are talking about upper bounds on the Kolmogorov complexity. So we also look at the following variants of Kolmogorov complexity and the Gödel problem. So the first problem, G greater or equal, is the problem that given a computable sequence and an upper bound on its Kolmogorov complexity, find a Gödel number. So if the slogan of Weihrauch and Rogers is correct, then this should be a problem which is slightly simpler than finding the Gödel number without the help of that upper bound. So you have somehow an additional advice here on the input side, the additional advice being that you have an upper bound on the Kolmogorov complexity. And then finally, there is this problem K greater or equal, and that is just the problem of finding an upper bound on the Kolmogorov complexity. Now, if you look at these four versions of problems that I've mentioned now, the Gödel problem G, the Kolmogorov complexity K, and these two variants defined here on the slide, then they are clearly related to each other. So if you can compute, for instance, the Kolmogorov complexity, if you can find a minimal Gödel number, you can find in particular some Gödel number. So that is why there is an arrow from K to G. If you can solve K, then you can use it to solve G. And likewise, if you can compute some Gödel number, well, then you can also find an upper bound on the Kolmogorov complexity, namely that Gödel number is an upper bound. And likewise, if you can find the Gödel number without additional advice, you can in particular find it with additional advice. Now, such a diagram as this one is exactly what we study in Weihrauch complexity. So we try to relate problems to each other. So given one problem K, can you kind of use it or abuse it if you wish to solve another problem? So can you use K to solve G? In this case for these four problems, it's kind of straightforward and obvious to see that that the corresponding arrows are correct, so that you can use the problem G, for instance, to solve the problem G greater or equal and so forth. But of course, we are also interested in separations. So in results saying that we can't reverse these arrows, or that certain problems are incomparable, and they are typically not as easy as positive reductions. Okay, perhaps before I continue defining Weihrauch complexity, is everything clear at this point, or are there any questions so far? So no questions so far. So I think there was some question whether you can see the transcription. I'm not sure what that refers to, but I hope you can see the slides. Okay, now here is a diagram that kind of visualizes what Weihrauch reducibility means. So this notion of Weihrauch complexity is defined in terms of a reducibility. Reducibility meaning that you can reduce one problem formally to another one. So here on the top we have two problems, F and G. Problems for us are just partial multi-valued functions, and we want to express what it means that one such problem, little f, can be reduced to another problem, little g. And so the intuitive explanation is, if you have a realization of the problem G, you can kind of use it once to compute F. And what does it mean exactly? That means that we have some fixed input processing operation K and some fixed output processing operation H, so that if you feed an instance P for the problem F, K transforms that into an instance for the problem G, and then a solution of the problem G together with the original input is given to H, which then has to produce a solution for F. And if there is a fixed computable K and H, so that this works, that whenever I plug in for G, say a program for little g, then F is computed in this way, then we say that F is Weihrauch reducible to G. Now, this is defined in terms of computable K and H. So if you don't like computability theory, you can also do the same thing topologically. So you can use a continuous K and a continuous H, which of course is only possible if these are topological spaces. And then we denote the reduction with a star. So the star meaning there is a continuous reduction. So it's something weaker than a computable reduction. Computability implies continuity, but not the other way around. And then we can kind of also approximate, so to say, between computability and continuity by using oracles. So this little p here in the reduction means that H and K can be chosen to be computable relative to some p. So which just means that the computation of H and K has the sequence p as an additional piece of information. So it can use this sequence P during the course of the computation. Now, it's not too difficult to see that all these relations that I've just mentioned here, all the three versions of Weihrauch reducibility, they are pre-orders, and so they induce an equivalence relation on problems that we denote with an equivalence symbol, index W, and the corresponding upper index. One can also show that this induces a lattice structure. So in other words, we can define the supremum and the infimum of any two problems within the structure. And so it's a lattice, and we call that typically the Weihrauch lattice. Okay, if that is clear so far, I will tell you a little bit about typical problems that we look at in this Weihrauch lattice. And then I will give you some motivation why this is a nice structure to look at and why we can do a lot of things with it before we finally come back to the Gödel problem and we try to classify it in the structure. Now, let me perhaps start from the bottom. So one typical problem that we can look at in the Weihrauch lattice is, for instance, just the limit map. So the limit map on bare space, so that is just the product space of the discrete space of natural numbers, which is called bare space. And so it has a metric and a topology and a limit operation. And that limit operation is just denoted by lim. It's one function we can look at. Another typical operation which is studied is called Weak-Koenig's lemma. So that's the second one from the bottom, WKL. Here the input is a tree. So TR stands for the set of binary trees. And the input is an infinite binary tree, and the output is just some paths in that tree. So these are two typical operations, and there are kind of slightly weaker variants of these two, which are here called closed choice on the natural numbers and compact choice on the natural numbers. And they will be particularly relevant for the classification of the Gödel problem. So what are these two problems, closed choice and compact choice, about? So in case of closed choice, the input is a sequence of natural numbers, and it's guaranteed to be not, the range of that sequence is guaranteed to be not the entire set of natural numbers. So at least one natural number is missing in that sequence. And the goal is to find one such number which is not enumerated in the sequence. That's called closed choice on the natural numbers. And then compact choice is a variant of that problem. So it's essentially the same problem. Find a number which is not enumerated in a given sequence, except that you also have an upper bound on the range of your sequence, an upper bound m. So your sequence is within the numbers 0 to m, and it's not the entire set from 0 to m, which is enumerated. And the goal is to find one number in the range from 0 to m, which is missing and not enumerated. So it's kind of a bounded version of the closed choice problem, and it's called compact choice for certain reasons. And then there are even simpler problems. I think I will not say too much about those. So these strange names here, limited principle of omniscience and lesser limited principle of omniscience, they have been coined by Bishop, who was doing constructive analysis. And so these are historical names, but these objects are very simple. So for instance, LPO is just the zero test. So you just get a sequence of natural numbers, and the question is that sequence entirely zero or not? Okay, so these are examples of problems. Now, what is all this good for? So I'll give you 3 other theories that this Weihrauch complexity is linked to, and these 3 are descriptive set theory, reverse mathematics, and computability theory, in the sense that we look at certain computational classes. In order to make these relations more precise, we need yet another concept that is called the jump. The jump, denoted by f prime of a problem f, is just the same problem f, but the input is weakened in the sense that if the input was previously described by a sequence of natural numbers, then it's now described by a sequence that converges to such a sequence. So in other words, you don't have a description of your object at hand, but you just have a sequence that converges to it at hand. That makes the input information weaker and the problem harder. If you want to solve the problem with weaker input information, it becomes typically harder. And the nth jump is denoted by brackets with an n. And so one nice observation is that the nth jump of the limit characterizes exactly the sigma 0 n plus 2 measurable problems. So this is meant to be sigma 0 n plus 2 in the sense of the Borel hierarchy. So that means on the lowest level, we have open sets, and then we look at the complements, which are closed sets, and then sigma 2 is the class of open sets, pi 2 is the class of closed sets, and sigma 3 would be the class of countable unions of closed sets, so sets that you also call F sigma sets. That would be sigma 3. So you can climb up higher and higher in terms of the topological complexity. And sigma 0n plus 2 measurability means that pre-images of open sets are sigma n plus 2 sets. So in other words, sigma 2 measurability sigma 1 measurability would be a continuity. So pre-images of open sets are open. Sigma 2 measurability would be pre-images of open sets are F sigma sets, and so forth. And so this can be characterized in terms of Weihrauch reducibility. And these problems that I just mentioned, Königs lemma, the limit problem and their jumps, and these closed choice problems and compact choice problems and their jumps, and LPO and LLPO and their jumps, they are sitting in the lattice structure as indicated in this diagram. And the entire lattice structure is kind of a refinement of the Borel hierarchy as shown in this picture. So these problems in the middle here, so these Kn and Cn problems, they have also been identified as a version of the so-called Paris-Harrington hierarchy, if you happen to know what that is. So that's a hierarchy of induction and boundedness problems. And these Kn and Cn are exactly the counterparts of those boundedness and induction principles. So these are notions from proof theory and logic. So it's perhaps far away from what you normally deal with. But perhaps the last slide is the most interesting one in the context of my talk. So we can also characterize classes of computable problems with Weihrauch complexity. So the notion of limit computability that I already mentioned previously can be also characterized exactly by lim. So a problem is limit computable if and only if it's Weihrauch reducible to lim. And the notion of finite mind change computability, also used in learning theory, can also be characterized by Weihrauch, by a Weihrauch reduction, in this case to closed choice on the natural numbers. So problem is Weihrauch reducible to closed choice on the natural numbers if and only if it's finite mind change computable. And there's also a way to characterize non-deterministic computations. Problem is non-deterministically computable if and only if it's reducible to WKL. So all these notions on the left-hand side, they have been studied and defined independently, but they can be characterized in terms of the Weihrauch lattice. Now, Gödel's result that the Gödel problem cannot be solved by a finite mind change computation can therefore be expressed in this way. The Gödel problem is not reducible to Cn. Now, in this talk, I will use Kn and Cn as benchmark. I want to classify the Gödel problem and its variants with respect to these benchmark problems. And that automatically has then interpretations in terms of computability, like indicated on the slide, in terms of descriptive set theory, in terms of proof theory. So in all these different worlds, you immediately understand something about this problem if you have classified its Weihrauch complexity. So before I move on to talk about that Gödel problem, are there any questions at this point?
I'll ask a question just to
please.
See if I'm keeping up. So Gödel's result was that a program is a sequence plus an upper bound on the complexity. Is that right? Was that Gödel's result?
No, Gödel's result. By Gödel's result here, I mean the result that you cannot guess a Gödel number for a given computable sequence, not even in the limits. So that would formally mean there is no finite mind change computability computation for this problem. So in a finite mind change computation, you would ask for a machine that takes the computable sequence as an input, and then the machine comes up with guesses what the Gödel number for that sequence is. But after finitely many mind changes, it would have to converge and stabilize to a correct guess.
Oh, okay, thank you for clarifying. I think that.
And so Gödel's result just means that G is not of that sort, and we can express it by such a Weihrauch reduction. That's just a characterization of it.
Okay, thank you for clarifying. Thanks.
Okay, and now any other questions in this direction? So I'm happy to take any questions. I understand that this whole aspect that I'm discussing here is completely new to you, so you might have very basic questions. I'm happy to answer any question that is there. I mean, obviously, I'm also not giving you all detailed technical definitions here, so some things might be tacit assumptions on my side which are unclear, so just please ask if there's anything. Okay, now here is the topological classification of these four problems which I have spoken about. Just to remind you, G is that basic problem given a sequence that is computable, find a Gödel number for it. K is the problem where we want to find the minimal Gödel number, and K greater or equal is just the problem where we want to find an upper bound on the Gödel number, and G greater or equal was the problem given an upper bound and the sequence find a Gödel number for it. And now this is the topological classification. So you see that here these equivalences come with a star, and the star means this is just a topological classification. So here we don't talk about computability, but we just ask, can we transfer the input information and the output information in a continuous way so that these things are equivalent or not. And it's not hard to see that if we are just talking about topology in a topological sense, these three problems are all equivalent, and namely they are equivalent to the closed choice problem on the natural numbers, whereas the fourth problem here, it's equivalent to the identity, which means it's continuous. It's a continuous problem. So that is perhaps, yeah. So why is this actually true? So, well, this is not too hard to see. We can ask the question even in a slightly refined way, namely, which is the minimal oracle among the empty set, the Turing jump of the empty set, the second Turing jump of the empty set, and so forth. So the first one would be the halting problem. The second jump is the halting problem relativized to the halting problem, and so forth. And so if we plug in one of these oracles for the star, so which is the best one that we can achieve here? And a relatively obvious answer is the second jump of the empty set. So that is the halting problem relativized to the halting problem. That will be sufficient to validate all these equivalences. So that means now these are computable equivalences, but the computations are allowed to use the halting problem relativized to the halting problem as an additional advice during the computation. Now, why is this relatively obvious that this is correct? Well, this is correct because the second jump of the empty set that makes totality decidable. So what is this about? So the problem is that if I give you a Gödel number, say I'll tell you 120,000, this is a Gödel number, you cannot recognize whether the program that belongs to such a Gödel number in general, whether that is total or not, so whether it stops on all inputs or not. And obviously only total Gödel numbers are candidates for answers here, because we are talking about total sequences as inputs. And even recognizing whether a Gödel number is total or not is not computable, but with the help of the second jump of the empty set, we can do it. We can decide totality. And if we can recognize whether a Gödel number is total or not, well, then we can find a Gödel number. So how do we do this? So imagine I'll give you a sequence like in the beginning 3, 5, 12, whatever, and your job is to find a Gödel number. Well, you just go through the Gödel numbers 0, 1, 2, 3, 4, 5, and so forth. And the first question you ask, is my Gödel number the Gödel number of a total function? If the answer is yes, well, then you just check whether on the first input it coincides with the first digit that is given to you, so say 3. Then you check whether on the second input it coincides with the Gödel number, with the sequence given to you, like 12, and so forth. And as soon as you recognize that your Gödel number is not correct, so if there is a mismatch between the input and what your Gödel number computes, well, then you just move on to the next Gödel number of a total function. And if you, after finitely many such mind changes, you will eventually have a correct Gödel number, where no longer any difference between the input and the output and the computation occurs. And then you are done after finitely many mind changes. And so that just is doable by finitely many mind changes, but with the help of this oracle. So you need the second jump of the empty set here. And well, that's rather obvious, and you get similar results for all the other problems. And you also get the reductions in the inverse order. So it's not just reducible to Cn, but Cn is also reducible to all these other guys. And so they are all equivalent. The surprising fact, perhaps, is that even though it seems natural to use the second jump of the empty set, this is not necessary. The proofs even work with the first jump of the empty set, namely with the halting problem. So we can take one jump away here and it's still correct. So the halting problem is kind of the minimal jump of the empty set that validates all these equivalences. And that's now no longer so fully trivial. So you need to do a little bit in order to see that this is correct. But it's not too hard. So let us look at an example. So here we want to show that the Kolmogorov complexity is reducible to the closed choice problem on the natural numbers with the help of the halting problem as an oracle. So as I just described previously, we go through all the Gödel numbers 0, 1, 2, and so forth, one by one. Then we check whether for a given Gödel number I, the numbers n, 0, 1, 2 are in the domain. So we can no longer decide whether I is a Gödel number of a total function. This is not possible with the halting problem, but we can at least check whether a given input n is in the domain, so whether the computation holds or not for that given input. And then we check whether it's the correct output. So if the output is correct for more and more numbers, then we keep on writing I to the output. And we move on to the next n and check whether that works. One of these tests fails, then we move on to the next Gödel number. And like before, this procedure stops going to the next I. When the smallest I is reached, that gives us exactly our sequence. So in other words, this is not much more complicated as what I described for the second jump. So this is not difficult to see. But the interesting thing is we can also go the other way around with the halting problem. So we can reduce the closed choice problem on natural numbers to the Kolmogorov complexity, and we can even reduce it to the problem of finding an upper bound on the Kolmogorov complexity. And here the proof idea is to use a variant of the set of random natural numbers. So these numbers have been defined by Kolmogorov. So basically, a random number in these terms is a number that cannot be, that does not have a program which describes it smaller than the number itself. And so this is a variant of the set of random numbers. In the classical definition, k is just fixed to be 0. So the variant here is that k here is an arbitrary parameter. And so this set R is a co-CE set, and hence it's reducible to the halting problem. So that means if we can compute the halting problem, if we have that as an additional advice, then we can also determine whether a pair Kn belongs to R, so whether it's random in this sense. And so perhaps I don't explain all the details here, so the proof is not too complicated, but the main idea is that we now exploit this set of random numbers to show that the closed choice problem is actually reducible to this variant of Kolmogorov complexity. And so if we can prove that K is reducible to Cn and Cn is reducible to K greater or equal, then we have established all the equivalences here in the third line, because the other reductions from K greater or equal to G and from G to K, they are trivial. So in other words, we have proofs for the two non-trivial ones, and the rest follows easily. What I've not explained is why G greater or equal is actually computable relative to the halting problem. So that means if I have access to the halting problem, I can actually find programs for computable sequences if I have an upper bound on the Kolmogorov complexity as an additional input. And for that proof, one can use a technique which is well known from algorithmic learning theory, which is called the amalgamation technique. So it's just a clever way of organizing the information, and that helps us to establish this proof. I think I will not go into the details here, so it's not too complicated, but I mean, if you want to know more, I'm happy to explain the proof afterwards. So this amalgamation technique is a well-known technique in learning theory, so it has been used by Weihrauch and others. So it's not my invention, but what is new is that we can use it here in this context of Weihrauch complexity to establish these equivalences. Okay, so basically what was known before was only that G is not reducible to Cn, which follows from Gödel's result, and that G greater or equal is reducible to Cn by a result of Weihrauch and Weihrauch. Okay, now this kind of settles the topological situation, and we even have optimal oracles for these topological results, but it doesn't settle the computability-theoretic situation. And in fact, from a computability-theoretic perspective, the situation is slightly more complicated. So remember, G, K, and K greater or equal, they were all equivalent to Cn topologically, but they are, if we don't allow any oracle whatsoever, so neither the halting problem nor the jump of it or any other oracle for that matter. So if we really want to have a pure computation without any additional information, then the picture is like this one. So that means the best upper bound we can find for K, G, and K greater or equal in terms of our benchmark problems. The best upper bound is Cn jump. So Kn jump doesn't work as an upper bound. And the best upper bound for G greater or equal is LPO star. So remember that LPO was the just the zero test, testing whether a sequence is entirely zero or not. And LPO star is a finite product of that problem. So we can use it any finite number of times in parallel, or we have to say beforehand how many times we want to use it. And that's an upper bound of G greater or equal. And so Kn wouldn't work as an upper bound. So actually, one can use here characterizations of these benchmark problems. So for instance, one can show that Cn prime, the jump of closed choice, is nothing but the lim-inf map on natural numbers. And so it's not too hard to see that the lim-inf map gives us an upper bound on the Kolmogorov complexity, because so suppose we do the following. So we look at the sequence that is given to us, which is a computable sequence, and we are trying to find a Gödel number. And we check all the Gödel numbers, whether they match longer and longer prefixes of the input sequence. And whenever we establish that a longer prefix actually matches a particular Gödel number, then we write that Gödel number to the output. So that would mean that we produce a sequence of Gödel numbers on the output side, where exactly those Gödel numbers appear infinitely often, exactly those numbers which match the input. Okay, so we don't get a stabilizing computation. We just have an infinite sequence which doesn't need to converge, but the numbers that occur infinitely often on the output side are exactly the correct Gödel numbers. And so lim_inf for such a sequence just gives us the smallest cluster point, so the smallest number which occurs infinitely often, and that means that would be the smallest Gödel number which matches the input sequence, and that means it's the Kolmogorov complexity of that Gödel number. So in such a way, we can actually establish these upper bounds. And on the other hand, one can prove that Kn prime wouldn't work as an upper bound, not even for k greater or equal. And the way to prove that is that we use yet another characterization that we have of Kn prime. So while Cn prime is equivalent to lim_inf, Kn prime is equivalent to the Bolzano-Weierstrass theorem on the natural numbers, which again just means we can find a cluster point in a sequence of natural numbers, but the difference is, in this case, the sequence of natural numbers is bounded. And well, the upper bound LPO star for G greater or equal can once again be proved by the amalgamation technique that I already mentioned earlier, and that G greater or equal is not reducible to K and can be proved by a technique called the finite extension method. So that's basically kind of a bare category argument. And finally, all these problems, G greater or equal, K greater or equal, G and K, can all be separated from each other with respect to Weihrauch reducibility. So none of these, they're pairwise non-equivalent. They are really distinct from the perspective of computability theory. So I show you the diagram again. So this is how these problems sit in the Weihrauch lattice. So what all this analysis shows, they are all really different, pairwise different. There are no additional reductions between these four problems than those shown in this diagram. And Cn prime is the optimal upper bound among the Cn and Kn problems and their jumps. Yes, so this is kind of the best we can hope for. So in fact, we cannot expect any equivalences here, because we saw earlier that topologically these upper three problems are equivalent to Cn. And so that would be the only candidate of a problem that they could be equivalent to. But computability theoretically speaking, they are not equivalent to Cn, as the best results are shown in this diagram. Okay, now what other questions can be asked in this context of the problem of finding a Gödel number? So I think one interesting property that I couldn't resolve yet is the question of whether the problem of finding a Gödel number is closed under composition. So this star here between G and G is a particular algebraic operation in the Weihrauch lattice, and it expresses a problem that is the most complicated problem that you get by first using G, then you can do some computation in between, and then you can use G again. So in other words, if you see this problem G itself as an oracle, it's what you can achieve by using G twice in the course of your computation. And one open question is that more than what you can achieve by using it once? What is not too hard to see is that if you reduce this composition to computable inputs, then it is equivalent, but whether or not it is equivalent in general, I don't know. So one reason why I was interested in these closure properties, which are mentioned here, is that they also have other implications or give us some interesting properties of G. I think I don't have time to go too much into this, but the problem of finding a Gödel number has a remarkable property, namely it is an effectively discontinuous problem, but it is not computably so. So now I would need to explain what that exactly means. So roughly speaking, effective discontinuity means that if you have a candidate for a continuous implementation of G, then you can pinpoint a witness for an input on which this implementation fails. And the question is, can you find such a witness in a continuous way or even in a computable way? And here the fact is that you can find it in a topological way, but not in a computable way. And that is a very unusual property. So normally, I mean, I wasn't aware of any natural problem beforehand that has this property of being effectively discontinuous, but not computably so. And G is the first natural problem that I know. One can construct artificial such problems, but the problem of finding Gödel number is somehow a natural candidate with these remarkable properties. Okay, so perhaps now there are only a couple of minutes left. So let me skip these slides. There are more interesting things to say here, but I will just leave you with these references here. And thank you for your attention, and I'm happy to take questions.